Right. Hello. I've been wanting to teach a bit of math for quite some time now, but my whiteboard is stuck at school, and you may know my whiteboard from previous videos where I also did math. That was when we calculated the value of pi with a Taylor series. Now we're going to do something just as cool and with an arguably better method of writing. As you can see, I have found an ingenious way to utilize my table. As you can see, it's covered by glass, and you can write on it, and you can erase it too, just with a simple tablecloth. So it's really great, and I have like something at the top of my desk that allows me to put my phone on top of it. So it's very convenient and everything just fits perfectly. So why don't I make a video where I utilize all these good, convenient placement and positioning of the phone and of this beautiful glass covered table. Right. So we're going to be doing something that is just as cool as I've said. We're going to be trying to understand little by little and also be able to prove a theorem. This theorem is known as Fermat's little theorem. Right. So it's not too complicated of a theorem to try to understand. And well, before we go ahead with this, I just want to say that my target audience here is basically anyone with a high school education in maths is gonna be able to understand this pretty easily as long as they focus and pay attention, hopefully. Even with a middle school background, that's still going to work too. Although this is not a topic that you study in high school at all, I think, it's still pretty useful. I mean, not useful. Maths is really not useful. I think around half of maths is just purely fun facts and like that can't be put to use. But this is one of the ones that has a little bit of use in cryptography especially. What does this theorem state? Well, basically it states that if you take any number a and if you raise it to the power of any prime number subtracted by 1, this is a number basically, and you subtract this number by 1, it's always going to be divisible by that prime number. Right. One more extra condition though. A must not be a multiple of P. So as long as you have everything else set up, then this is always guaranteed to be true. What do I mean by divisible? What I mean by divisible is you can divide this number and this number, and you're going to end up with another whole number basically. So an example is 4 divides 2. Wait, no. 4 is divisible by 2. Yeah, divides and divisible is different. They have different definitions in terms of maths. But yeah, don't worry about the other word. 4 is divisible by 2 because we can have 2, and 2 is a whole number. That means that this statement is true. 4 is divisible by 2. In other words, I mean not in other words, in another example, 3 is not divisible by 2 because that's going to give a fraction or a decimal. It's not going to be a whole number. So 3 is not divisible by 2. Right? So what this thing says is that if you divide these two numbers together, you're always going to end up with a whole number. So let's see this thing in action, right? Let's set a to be, I don't know, 2, and let's set p equal to 5. This thing works out. 5 is a prime number, and 2 is not a multiple of 5. Oh wait, a must not be a multiple of p. Sorry about that. Yeah, 2 is not a multiple of 5, so this thing is guaranteed to work. So let's try it out. 2 to the power of 5 minus 1, which is 4, subtracted by 1 is divisible by 5. What's 2 to the power of 4? Well, that is 16, and 16 subtracted by 1 is 15, and voila, 15 is divisible by 5. So pretty cool, right? One important application of this, like I said before, is with cryptography, and that's because you can simplify very big numbers. For example, prime here could be, I don't know, a number like 101, for example. I think 101 is prime. I hope it's correct. So you can say 2 to the power of 100 subtracted by 1 is always going to be divisible by 101. See, you wouldn't have known this fact if not for Fermat's little theorem. It's also very difficult to prove this fact by hand or even by calculator, because it's going to have to deal with huge numbers. It might crash, but because of this little convenient trick, we automatically know that this number is divisible by 101. And we can use that fact in other calculations, which is important, again, in cryptography. The simplification of like really big numbers, basically. Right. So let's delve deeper, okay? What is written down here is basically a sentence. It's English, basically. But people in math, they write things in a completely different language. That's because it saves space for textbooks and other math books. Okay, so this thing, in math terms, in math lingo, would basically be equivalent to, I don't know, my arrow is a bit weird, but you get the point. Is equivalent to a to the power of p minus 1 is congruent to 1 modulo p. This thing is basically exactly the same as this thing, but as you can see, it is much shorter, much more compressed. Basically, what does this thing say? It says, it is a statement, basically. This is not an equal sign. You should not treat it as an equal sign. It has 3 bars instead of 2 bars, and it's 3 bars for a reason. This essentially talks about a statement, and it is not like equal sign, so you can't like move things around, basically. This thing is a statement. It states that the number on the left side subtracted by the number on the right side is divisible by the number that comes after the 3-letter word mod. So I hope you can see why this is exactly the same as this. AP minus 1 subtracted by 1 is divisible by P. That's what basically these things says. So this statement is made up of 3 components: this number, and this number. And depending on the positioning of these numbers, it can tell a different story. Alright, so let's continue. We're gonna get rid of this English word now, and we're just gonna have to rely on the shortened math form that everyone in the math department uses. At least you know what it means now. We're just gonna set it up on top over here. And I'm also gonna stress that A is not equal to a multiple of P. Alright, let's take a look at another example of how we might be able to apply this mod statement thing. Just some examples to let you get used to it. An example would be 5 is congruent to 1 mod 4. And this is definitely true, because 5 subtracted by 1 is 4, and 4 is definitely divisible by 4. Something that is not true would be, for example, 4 is congruent to 1 mod 2. This is definitely wrong, right? So whenever you have a correct statement like this one here, we say that 5 is congruent to 1. And mathematicians, they write that with 5, and they have this squiggly line and 1. This means that 5 is congruent to 1. This and this basically mean the same thing. While 4 cannot be congruent to 1. This is definitely not true. Only correct statements get to have this sort of congruence relationship that we are talking about. Another important thing to note is that we can essentially apply algebra to this thing. We can instead turn this not into a statement, but we can turn it into a question. We can change 5 into x, for example, and now we have to solve for x. Well, clearly, I mean, one answer, even if like I erased it before and like you already know it in your head, and you already know it in your head from like before, you can still probably figure this out on your own. The answer is obvious. 5 subtracted by 1 is divisible by 4. So 5 is an answer here. But it turns out there are also multiple answers as well. For example, 9. 9 is also part of x, because if you put 9 here, 9 subtracted by 1 is 8, and 8 is definitely divisible by 4. So this thing is a solution as well. And you're going to notice that these solutions, they are going to be 4 apart, which means we can easily figure out the next solution. That's going to be 13. 9 plus 4, 13. And well, you have it. There you have it. 13 subtracted by 1 is 12, and 12 is divisible by 4. So there can be multiple solutions, and this is why the statement at the top has multiple solutions. We can set A as 1 or 2 or 3 or 4, as long as it's not a multiple of P or 5, and it can go on forever, essentially. And all of these things, if you put 5 in here, if you put 4 in here, if you put 3 in here, it's all going to be true. So so the solution for A is all these numbers except for anything that is a multiple of P, right? So that is how you algebra things out if you think of things algebraically. If you think of A as a question, you can think of A as a solution too, and you can find a way to figure out a solution. And that is what we are going to be doing throughout the course of multiple videos. We're going to take a look at some basic properties of the congruence relationship now. There are 3 important properties. Number 1 is that A is always congruent to A. And A is any number basically. So why is this true? Well, let's take a look. Well, let's try to translate this basically. What this means is that A is congruent to A mod n, where n can be any number, doesn't matter. And let's translate this again into English. A subtracted by A is divisible by any number n. Right, so what is A minus A? Well, that's obviously 0, right? And 0, is it divisible by n? Well, clearly, yeah. If you have 0 at the top and at the bottom you have 1, or you have 2 or 3 or any number at all, that's going to give an answer of 0. And 0 is a whole number, it's not a fraction. This means that 0 is divisible by any number. And if this statement is true, this statement is true. And if this statement is true, then this statement is true, right? So that is how you prove the first property, that is, any number is always congruent to itself. Second property, if A is congruent to B, then B is congruent to A. Right, so this wouldn't be as easy as the first one to prove, but it's still easy, right? So what does this mean? If we translate this to English, basically, it means that A subtracted by B, if you divide it by a number n, you're going to get a whole number k. We're going to set k as a whole number. I'm just going to abbreviate it like that. Right, so we know that this is true, right? If A is congruent to B, that means we must show that B is congruent to A. Well, what if we multiply this thing here, this statement here, by -1? If we multiply it out by -1, we're going to get negative A plus B, divided by n is equal to -k. Well, we can essentially move this here and move the A there, right? I mean, there's no problem there, clearly. So that would give B subtracted by A divided by n is going to give out -k. This statement is equivalent to this statement because we multiplied by -1 on both sides. That doesn't change a thing. We preserve this equation, basically. Now, what does this say, basically? If you take B and you subtract it by A, you divide that by a number, you're going to get -k. What is k? K is a whole number. What is it negative of a whole number? Well, negative of a whole number is still going to be a whole number. This means that this statement is true, right? And if this statement is true, that means that B is congruent to A. Because what does this mean? This means B is congruent to A mod n, which means that B minus A should be divisible by n, and that is exactly what this thing here states. So, cool. If this is true, that means that this is true, because you can multiply it by -1 and everything would still work out just fine, in a mathematical sense, basically. Alright, last property. Third property. If A is congruent to B and B is congruent to C, then A is congruent to C. It's getting much more complicated each time, but it's still simple enough to prove. What does this mean? It means that if A minus B is divided by n, it's going to give out a whole number k. What does this mean? If B subtracts C divides by n, it's going to also give out another whole number, but we're going to denote it as k prime instead, because these whole numbers may not necessarily be the same. It's just that it gives out a whole number, could be a different whole number, who knows, right? Right, so how do we prove this then? Well, why don't we try adding these two things together, right? If we add A minus B over n plus B minus C over n, that's going to be same as adding k and k prime. Alright, so let's add this thing together. A minus B added by B minus C divided by n is going to be equal to k plus k prime. And look, the b's cancel out, right? And what you're left with is A minus C divided by n is going to give out a whole number plus a whole number, which is a whole number, basically. So you can erase this and say k, because k is a whole number. A minus C divided by n is equal to k, a whole number. This means that this thing is true. And again, that means that we have proven statement number 3. Now, statement number 3 is the most useful of them all. And we're going to highlight that with a simple example. Basically, if we know that 100 is congruent to 1 mod 3, This is true because 100 minus 1 is 99, and 99 is divisible by 3. We can simplify things very greatly. Let's say we have 100 multiplied by 5 is congruent to, well, I have no idea, x mod 3. So we have no idea what x is, and x is something that we need to calculate. Well, basically what this thing states is that if A is congruent to B and B is congruent to C, then A is congruent to C. It essentially means that we can substitute things out. We can get rid of the middleman, which is B here. We can get rid of the middleman, and it'll just be A and C. What is the middleman in this case? It's going to be 100, right? Because 100 is there in both equations. It is in A is congruent to B, and B congruent to C. 100 congruent to 1, 100 congruent to x. We can get rid of the middleman out. And we can directly link A and C together. So that means that 100 is congruent to 1. We can substitute 1 in for 100. That's going to put it right here. 1 times 5 congruent to something mod 3. Well, we can easily figure this out because 100 just became a really small number. The answer is 2. X is equal to 2. This is why this thing is very useful. It simplifies a bunch of stuff. And you can substitute things in if you know that they are congruent with one another and they satisfy this relationship. Before we leave off, we're gonna try to answer at least one part of this theorem, which is gonna be this part. Why is this thing true? Why is this a necessary condition? Let's think about it first, okay? We're gonna need another property. It's not part of the 3 basic properties, but it is a property nonetheless. And that is, if you take a number p, that's always going to be congruent to 0 mod p. Take note that these things must be the same. Why is this true? Basically, this thing means that p minus 0 divides p is always going to give out a whole number. And we know this is true because p minus 0 is just the same as p, and p divided by p is definitely going to be a whole number because the top and bottom is the same. It's going to cancel out, and actually it just gives out 1. And 1 is definitely a whole number, so this thing is true. Right, so we know that this is true now, right? Well, let's apply that to this principle over here. Let's assume that A is a multiple of p, right? If A is a multiple of p, then what could go wrong? Alright, let's test this principle out, right? If A is a multiple of p, that means we can write A as, well, some number times p. That is what it means to be a multiple of p, right? This thing is true if A is a multiple of p. Now let's substitute that in here and see what we get. So we have kp to the power of p minus 1 is congruent to 1 mod p. Alright. But take a look at this thing. P is congruent to 0 mod p. P is congruent to 0 mod p, and we have over here p is congruent to 1 mod p. What can we do? We can get rid of the middleman. The middleman in this case is p. Just like we did before on the previous example, hopefully you haven't forgotten yet. Since p is equivalent to 0 mod p, we can substitute p for 0. We can get rid of the middleman here and directly add 0 there. But this would mean that k multiplied by 0. Any number multiplied by 0 is just 0, right? And 0 to the power of anything is still just going to be 0, so we can just get rid of this as well. And what we have in the end is 0 is congruent to 1 mod p. Now this is definitely not true. Why? Because this would mean that 0 subtracted by 1 is always divisible by p. This statement is obviously wrong because negative 1 divided by p is never going to give out a whole number, because the prime numbers, they start with 2, 3, 5, 7, anything that you put in here that is a prime number is never going to give out a whole number. It's always going to be a fraction. So it's going to be 1 over 2 or 1 over 3 or 1 over 5 or any of it like that or anything like that. So what went wrong? We assumed that A is equal to a multiple of P, and that gave out a wrong answer. An equivalence, an equivalence or a congruence. Congruence and equivalence is basically the same thing in maths. Some textbooks use congruence, some textbooks use equivalence, but the equivalence is wrong if A is a multiple of P. So we at least have proved one part of this theorem, and across the next couple of videos we're going to prove the rest of this theorem. And we're going to use group theory to do that. It is a new branch of mathematics that you'll have to learn. So it's going to be exciting if you enjoy maths. And hopefully you enjoyed this thing too. I don't know if I should call it a lecture. Just seems like, I don't know, I'm just teaching like this little topic here. And hopefully it's going to give you a better understanding of maths. But yeah, next video is going to come out real soon, I expect. So if you enjoyed this video, well, keep how do you say that? Keep a lookout for the next video. Alright, see you next time.